It's really a brief discussion. It's not a history. I've changed it since I gave a title before and decided that the history of each of these would involve too much repetitive material because it's been discussed a lot before and elsewhere here, and here as well as elsewhere. So what I would like to talk about now, and I can make this very brief, is the major problem that has been referred to over and over again and even discussed here today of niobium, thin film niobium, and what has to be overcome. And not that there are any new techniques for creating films, but it is important to focus on the steps we take to understand what we have so we know where we're going. So I will try that. Why do we need to develop thin films with bulk-like performance? Go to the second bullet first. It's if we have a high HC1, or let's say a clean film, because it's not simply HC1, that's the best choice for the first superconducting film in a multilayer structure. If you build up too many low HC1 films, you will eventually run into problems of thermal issues. The other reason really is, I think, becoming understood now, but for a long time there was a misconception that the basic issue was saving niobium, the cost of niobium. It's really that you can use materials like aluminum or copper, both are relatively inexpensive in high purity form, in shapes that are quite formable, much cheaper to make, and most importantly, you can integrate cavity cryostat functions so that the overall cost of the LINAC module is dramatically reduced. I step out on a limb talking about factor of 10 sometimes. A lot of people will disagree with that. But many functions can be engineered out of the structure, such as that you have with sheet metal, such as microphonics, the various acoustic modes that occur in flimsy structures like that. Ponderomotive oscillator, we call these Lorentz force detuning these days. If you imagine a cast structure with fluid heat exchange surfaces cast in, as well as stiffening ribs and so on and so forth, the cost of doing a one-shot casting like that is vanishingly small. The ultimate issue is surface preparation of the inside, as it is with any structure. So those are two, I think, overriding reasons. And I'm not going to talk much about conventional sputtering, even though I'm comparing that to energetic condensation. Everyone is familiar with the type of severe Q droop, the non-quadratic losses that you get within niobium films. The CERN group over many years has done a fantastic job of analyzing and doing experimental work on those issues. So I won't go into those. But this, I would also say that is probably the only reason I can think of that has kept niobium copper cavities, thin film niobium, used in actual applications for beta equal 1 applications anyway, since LEP. I think there's no reason for it other than that. I've already mentioned this. Much work has been done with examining the non-quadratic losses and nonlinearities in using various techniques by many laboratories. They've all been discussed, including here before. The major cause, really, that I think is in everybody's mind for the nonlinear behavior is the very short electron mean free path, and it will severely depress the lower critical field. And this is aggravated, of course, by someone already mentioned today, rough surfaces, where the field enhancements will allow it to enter more quickly. And then, as Alex pointed out, there's also the other issue that involves the energy gap, but they both involve the primary cause still is a low HC1. I mean, a low mean free path, electron mean free path. And you could lump all the things that cause electron scattering into two. One is the two groups. One is in case of sputtered films, the sputtering gas inclusion, and the other would be structural defects from the niobium itself, niobium film. And this is a table from one of the CERN papers that is a very nice study showing here for the conventional argon that everyone uses a very high gas content. For krypton, which they have also used and gave some improvement in actual RF results. Here, the improvement here in triple R is significant, but not dramatic. And I think that's probably due to the fact that even though there's this reduction in gas content and there are different scattering sources anyway, this is probably dominated by structural defects from the nature of sputtering as a deposition technique. And yes, I just mentioned that. There, again, just to repeat, this is a little history. The two film structures that were explored by CERN were a fiber structure, which they created by oxidizing the copper surface to destroy epitaxy. And then they've also looked at large grain heteroepitaxial structures. Interesting, let's see, I think I mentioned on the next slide, maybe, the mean free paths. Here they had one sample, this is a columnar structure. I'm sorry, they're both columnar, but this one is a fiber structure. And the other was a single, I'm not saying, heteroepitaxial. And if you look at in both cases, the grain dimensions can't account for this kind of a triple R. If you had a 1 micron grain, the type of electron mean free path you might expect is on the order of, it's greater than 500 nanometers. I'm sorry, it's greater than a triple R of 500 rather. And substantially greater, the scattering of a grain boundary isn't perfect anyway. The transparency depends on the grain angles on either side. In the sputtering case, since the sputtering energy is so low in terms of deposition for the condensing film, the predominant for a high melting point metal like niobium with a very low substrate over melting point temperature ratio, the predominant source of defects, electron scattering defects that you would expect, both from simulation and from very extensive literature, would be dislocations, voids, and of course impurities, but the structure of low films deposited for any metal on a low substrate, a low temperature substrate, is very poor for a high melting point metal. It's surface roughness, we've already discussed that. Geometrical effects, also the angle of incidence that's been studied in terms of RRR here at this lab, at Lignaro and elsewhere, and shown to, for the more glancing angles, having a more severe effect in reduction. And these effects can be avoided. Surface roughness is an issue in any process. There's some things we don't know about sputtered films. When we measure RRR of either on an insulator or removal from copper, you're measuring the whole average RRR of the whole film. And we have no idea of how this varies from the onset of nucleation, where we know the RRR is extremely low as the film gets organized, to what its final value is at the penetration depth, which is what you care about. So what is the RRR and the penetration depth? Well, we've tried, I'm jumping ahead a little bit, we've tried to come up with schemes for measuring this easily. There aren't any, but there are some schemes which we're exploring for doing it with a little more pain, but it can be done. We don't have that in hand yet. But the other interesting thing is, if you have, in the heteroepitaxial case, you have different, the niobium picks up the nearest lattice match of the underlying copper grain. And this will start the film off with a lot of misfit dislocations that would vary from one grain to another. We don't know what, and also the fact that you're depositing each grain at on a different grain surface, that is a different crystal plane, as it continues its columnar growth to the penetration depth. None of those things we really know. With energetic condensation, we can avoid many of the problems with conventional sputtering. And here we're looking at just one form of energetic condensation, which is that of niobium ions deposited in vacuum at controlled energies. Now, the two major differences between this technique and deposition by conventional sputtering are that the one is the energy added to the film as it's condensing layer by layer, and the other is a lack of gas ion scattering, and in addition to gas inclusion in the film.